Okay, last set of notes for Unit 6. Okay, so what we're going to do is we're going to jump straight into significance tests. And so we've done significance tests for one proportion, and now we're going to do this for two proportions. So normally the way that we're going to see this when we have two proportions is our null hypothesis. We're going to say that our proportion of 1 is going to be equal to our proportion of 2. Now, this is a difference between proportions. So we can also see this as P1 minus P2 equals 0. So hopefully you can see that we're saying the same thing here, right? If we move the P2 over, it looks just like this. So our null hypothesis is that they are equal. Okay, so our alternative hypothesis, we're normally going to see it like this, and this tells us we have a difference. And so this value that can go in here is not really subtraction. This could be greater than or less than or unequal to, so it can be any one of these. Or we can see it as P1 minus P2 is going to be, again, whatever value we have here, so greater than, less than, or unequal to 0. So I wrote this a little bit funky, so don't look at this as a true subtraction. Look at this as you're going to input your sign, whatever's going to happen. And so we'll see this as a difference saying P1 is greater than P2 or P1 is less than P2. Okay? So this is a little bit different. So when we talk about our conditions, with our normal condition, this is going to be new. And this is new because now we have something called P sub C. And this P sub C is going to be that our values are going to be combined. So let's pop down here really quick and then we'll come back up. So I have this pooled proportion. That's what it's called. It's not called a combined population. It's called a pooled population, which means we're going to put these together. So this pooled sample proportion, it's really our population. We're taking everything and we're combining it. We use this value of P sub C. And so when we have this pooled, so think pooled is combined, we're going to take our sample, our successes from our first population and our successes from our second population, and we're going to put this over the total combined or pooled population. Okay, so this is what we're looking for when we have this pooled population. And we have this actually on our formula sheet. So if we look over here on our formula sheet on the back page, we have P hat sub C, and it's just, it tells us right here, it's our two successes over our two sample sizes. Okay, so now we have this new value of P sub C. So what we're saying is that when we have a normal distribution, our sample size of the first one times our pooled proportion. Now, when we come up with this proportion, I'm calling it a combined population because that's what this is. This is the combined population of your two samples, right? So we're combining our two samples. When we look at our normal condition, we take our normal times our pooled proportion, and this has to be greater than or equal to 10. And then, of course, the complement, so 1 minus P sub C. And then our second sample, same thing. Okay, so this is new. I'm going to highlight this because this is something that we're going to do a little bit differently. We're not just going to take each individual sample. We only do this when we're doing a significance test. All right, so random, they both have to be random selection or random assignment. This is the same. Independence, this is also the same. We're testing one sample against the overall. And then, of course, this is important. Only check for sampling. If you check for an experiment, you would be marked off. All right, so we get down here for this pooled proportion. We only use a pooled sample proportion to calculate the standard deviation because we always assume the null hypothesis, so this one, of no difference is true. Therefore, we assume the successes come from the same pool. So that's why we do this. This is only used for significance tests. We use this to check large counts and to find the sample standard deviation. So we're going to use this two ways. Large counts, which tells us it's normal, and our sample standard deviation. All right, so calculating our p hat. So here's what we have. We have that our z statistic, when we have a difference, is p hat 1 minus p hat 2 minus 0. And the reason we have this minus 0, so you don't even have to put this, is because we're saying they're different. So we're using this, right? We're saying that the difference between the two of them is 0. And this goes over my standard deviation, which is my pooled. Remember, it's my pooled standard deviation. So 1 minus p sub c over n1 plus p sub c, 1 minus p sub c over n2. So you see that your sample size is going to affect your standard deviation. Okay? Now, another way that you're going to see this, and I'm going to write this right here, is you'll see p hat 1 minus p hat 2 over p sub c, actually this is p hat c, 1 minus p hat c times 1 over n1 plus 1 over n2. So what did they do here? They just factored out this numerator because you have it twice. So they factored out the numerator, and when they factor out the numerator, all you're left with is your denominator with your samples. This is the way that you see it on the AP formula sheet. And I'll show you where that's at. So if we look at our formula sheet, we're up here under sampling distributions for proportions, and what we see for two populations, over here, our sample statistic, we see this right here. All right, so that's our pooled, and here's how we find our pooled. Okay. Oh, one other thing that I wanted to talk about. So what you're going to find in this case, so here I wrote this as just p sub c, and here I wrote this as p hat sub c, and you're going to see this either way. Now, normally we say it's super important that we talk about it as listing the right one, but only because it's our pooled proportion. So we can say that our pooled proportion takes our sample data. So P sub C, no matter which way you look at it, is your sample data. So you can write P sub C either way. All right, let's do an example. Is there a significant difference in the smoking habits of younger and older generations in a random sample of 600 adults? So I'm just going to go ahead and do my conditions right here, or my communicate as I go through this. So random sample of 600 young adults. So I'm going to say right now that my population 1 is going to be proportion of young adults who smoke. And I'm kind of reading ahead on this because I'm assuming that that's what this is going to be about. And my proportion 2 is going to be our older generation. So proportion of older adults who smoke. All right. So in a random sample of 600 young adults. So N1 is going to be 600. It was found 180 of them had smoked in the past week. So X1 is going to be 180. In a separate random sample of 500 older adults, so that's my older adults, 500, it was found that 185 of them have smoked in the past week. Conduct a significance test at the 5% level. Okay, so what I know here is my percent C is going to be 95%, and my alpha is going to be 5%. It doesn't tell me this 95%, but I know that because my significance level is 5%. Okay, so here's what I know. I know that my null hypothesis, I'm going to say P1 equals P2. And then for my alternative hypothesis, let's go here and look at this. Conduct a significance test to determine if there's evidence to suggest that the proportion of smokers differs between the young adults and old adults. It doesn't tell us if one's greater than or less than the other, so I'm just going to have a two-sided interval here, and I'm going to say we want to know if it is not equal. Okay? Now, because I'm doing this difference, I have to find my pooled proportion. And so this is going to be 180 plus 185 over 600 plus 500. And that value, let's see, what do I have? 365 over 1100. All right, so my P sub C is going to be 0.332. Okay. Let me go in here and do my conditions. I don't know if I'm going to have enough room on this. So conditions, it tells me I have an SRS of sample 1 and I have an SRS of sample 2. I read that up there. All right, so I'm going to check my independence. So with my independence, my first sample was 600, and that's greater than or equal to 10% of all young adults. And then my other sample is 500, and that's obviously greater than all older adults. Okay, now I'm going to check my normal condition. And my normal condition is going to be 600 times 0.332. This is my pooled proportion. This is the thing that's different. And this is greater than or equal to 10. And then my other sample, 0.332. And I know that you've done this. This is tedious. You don't want to do it anymore, but you have to do it. So just do it. All right, so we're going to go over here to calc. So what I have here is a 2-prop Z interval. 2 samples for a population. We're looking at proportions, and we're going to use Z intervals. So here's the test that I'm running. So when I plug this in, I'm just going to go ahead and write this down so we have it. It's P hat 1 minus P hat 2. So now it's a difference. And then here I'm going to have P sub C, 1 minus P sub C over 1 over N1 plus 1 over N2. Okay, so I'm going to plug all of this in my calculator. I actually didn't calculate P1 and P2, but I can do this up here. So P hat 1 is going to be 180 divided by 600, so 0.3. And my P hat 2 is going to be 185 divided by 500, which is 0.37. Oops, 0.37. Okay, so I have 0.3 minus 0.37 over my pooled proportion, so 0.332, 1 minus 0.332 over 1 over 500 plus 1 over 600. Oops. Hold on. I'm not going to waste your time. I already know what this value is. My Z-star value. Or it's not Z-star. My Z value is negative 2.4. Sorry. Yeah, 2.455. All right, so that's my Z-star value. Okay, I'm out of room, so I'm going to go over here to this blank piece of paper and continue over here. So here's what I have. I've got this normal curve, and I have a value here of negative 0.2455. I have a value here of 2.455. Remember, I said my alternative hypothesis is P1 does not equal P2, so this makes it two-sided. So I need to know this, and I need to know this. So I'm just going to do just the lower bound. So if I do the lower bound and I do normal CDF, negative 2.455. And what I get here is 0.007. Now this is just my lower bound, so I have to multiply this by 2. And what I get is that my p-value, remember it's a test, so it's a p-value, is 0.014. Okay, so I'm going to go in here and do my conclusion now. So my conclusion, because our p-value of 0.014 is less than our significance level of 0.05, and I'm going to show the inequality. 0.014 is less than 0.05. We reject the null hypothesis, or you can just say H sub 0. We have convincing evidence that the difference hold on, the difference the proportion difference between young adults and old adults who smoke are different. Remember, all we care about is P1 equal to P2? So we reject the null because we say there is a difference. We don't have to talk about what the difference is. That's just the difference. Okay. All right, let's go into the second part now. Okay, so if I get back to this, it says, what type of error could we have made in the sample above? So I'm going to just go ahead and sketch this. This is type 1, this is power, this is type 2, and we rejected the null, right, where we could have accepted. So when we do this, we could have done it incorrectly, but when we rejected the null, we should have accepted the null if this was an error. So this is going to be a type 1 error. So because we rejected the null, we could have done it incorrectly, resulting in a type 1 error. And I'm going to put some context on this. So meaning the young adults and older adults have the same smoking habits. Okay. All right, last one. Find a 95% confidence interval using your calculator, interpret it, and explain how this means. So this is what we did in the other lesson. So I'm just going to plug this right into my calculator. So stat, test, to proportion z interval. This is what I have. And I know my sample 1 is 180 over 600 and 185 over 600. And this is 95%. So here is our confidence interval. Hold on, I'm going to check this again because that's not what I have written down. 2 prop z interval, 180, 600. Oh, that's why. 180, 500. There we go. Ah, that's better. Negative 0.126 and negative 0.014. Okay, now remember that our value that we were looking for here when we calculated all of this out was 0.014. This was my p-value. So the other thing that we're going to say here is interpret the meaning and how it confirms your results from above. So our p-value, let me just put this right here. Our p-value is 0.014, not negative, but this is the positive. So what I'm going to say is because our interval negative 0.126 to negative 0.014 does not contain our p-value, we would reject H0 when alpha equals 0.05. I don't know if that's necessary, but if we change this confidence interval, then we could get that. So bottom line is the p-value does not fall into the interval, and we would reject it, which is what we've already set up here. We're going to reject the null. Over here, we're going to reject the null because this value is less than our significance interval. Okay, so we did this in class the other day where we said if we've got a p-value, we've got an interval. If it doesn't fall into the interval, we reject. We did this up here mathematically, and then we went ahead and supported that. Okay, and then I've already done this today. You guys can figure this out. This is our 2-prop z-test when you can pull this on your calculator. And what you'll see is if you plug this in, when you plug this in, you're going to get your pooled proportion as well. So you'll get that too. Okay? All right, we'll see you in class.